Welcome back, everybody. So for today, let's continue with more questions. I will solve that question that I was stuck on last week. So I'll say let A be a ring and M a module. I need to prove that M mod IM is isomorphic to A mod I tensor product M. So how do I do this? I can prove this many ways. One way of showing it is that I want to prove M mod IM is the universal object of the bilinear maps through A mod I cross M. Okay, so A mod I is an A module, M is an A module. We can form the tensor product. Well, I want to prove the tensor product has this isomorphism. So let N be an A module, and suppose we have this phi map. Suppose it is A bilinear, so I want to prove M mod IM is the universal object of A mod I cross M. I want to prove that phi factors through M mod IM, and so there will be a map I have to define and show that it factors through. So I need to prove A mod I cross M goes through here, and there is a unique map through N this way, such that we have commutativity. This diagram commutes. I claim that G is the map taking this to M mod IM, and so A plus I comma M goes to A dot M plus IM. So I need to find a special map psi that is unique. Sorry. So how do I prove that there is a special map psi? So here we are. So let's say psi goes from M mod IM to N. I don't know what psi is. I don't even know what N is. It's very general, but I do know that psi of M plus IM has to be something in N. I don't know what that is, but I do know that psi of M plus IM is the same exact thing as psi of G of 1 plus I comma M. So you see that M plus IM is the same as 1 times M plus IM. And so that's the same thing as 1 plus I times M plus. Yeah. So it's the same thing, actually. So psi of M plus IM is going to be the same as psi of G of 1 plus I comma M. So what is this map going to be? So remember, I want this to be a commutative diagram. So psi of G should equal phi of 1 plus I comma M. And therefore, I'm claiming that psi going from M mod IM to N should be M plus IM goes to phi of n plus I, comma n. And that is perfectly correct. This is literally the map that I have. So if you have that phi is a bilinear map from a mod I across M to N, then I can define a map psi that makes this diagram commute, but psi must be unique. Psi is precisely this map, and therefore done. I am done. So there is a linear map psi going from M mod IM to N, and this psi is unique. And so it shows that every map from A mod I across M to N factors through this G with this unique map psi. And so we are done. So that means M mod IM is the object that factors through every a bilinear map. I will say phi, going from A mod I across M to N. Thus, we do have an isomorphism and that isomorphism is unique. Okay, so that was one way to proving that A mod IM. I'm sorry.
You skipped the tensor part. Yeah.
Yes. Yes. So A mod I tensor M is in fact isomorphic to M mod IM. There are other ways, I'm sure, to prove it, but this is just one. Okay. So that's number 2. Let's try to do number 4. So let Mi, or let's say I, is inside this index set capital I, be a family of A modules. And I'll say M to be their direct sum. I need to prove that M is flat if and only if each Mi is flat. So how do we do this? I'll say this is in black. And then let's try to solve what's going on. Okay, so M, AI, and M be as in our hypothesis. How do we prove that M is flat if and only if each of the factors is phi? So remember, let's say P and Q be A modules, and let's say F going from P to Q is injective. So F is an injective A module homomorphism. So I need to prove that F tensor A P tensor M is injective if and only if each Mi is flat. So how do I do this? So I want to give a better idea of what this looks like, these two modules, because actually tensor product is very abstract. It's hard for us to understand how tensor products really behave. It's rather strange things can happen. So I would actually like to relate this idea, this module, to something that's a little bit easier to understand. So, so ignore that for now, and let's start all over. So remember, there is an isomorphism. This is part of the textbook chapter, the textbook chapter 2. Etienne McDonald go over this. We went over it too. But as a reminder, there is an isomorphism like this. So remember, M is the direct product of all these MIs. So there is a isomorphism from this tensor product to this direct sum. So how is that isomorphism going to be? Well, I'm not going to tell you the map on every element, but I will tell you the map on every generating element. So P tensor, so an element of the direct sum is going to be, is going to be something like this. So there is a, excuse me, there is a isomorphism that looks like this. P tensor Mi, like this. Okay? And so there's also another isomorphism, very similarly, Q tensor A M to this direct sum in a very similar way. It's the same exact map. Q tensor I going to Q tensor Mi like this. So I will show you later why these maps are important. So we had this map here. So there's another map that's, again, as I said, a little bit easier to wrap our heads around. So let's start with this new map, F tilde, I will say. F tilde goes from the direct sum like this to the direct sum. I'm sorry, this direct sum like this. And so F tilde acts very naturally. So each P tensor Mi goes to F of P tensor Mi. So F tilde is not an isomorphism, but it's a very nice map. Notice that F tilde is actually the direct sum of the maps F tensor 1 Mi. And I also want you to realize that this F tilde is injective if and only if each of the F tensor identity of Mi is injective. Okay, and this is true if and only if each Mi is flat. Okay, so let's go back to our original question. How do I prove that this map P tensor M F tensor 1 to Q tensor M is injective? How do I show that this map is injective? I'm sorry, what are the conditions for this map to be injective? Well, I don't know. I do not know that answer. But there is that isomorphism G down to P tensor Mi. And there is that isomorphism G prime down to Q tensor mi. Okay, how do I connect this diagram? Actually, this diagram is connected by this F tilde. This F tilde makes this diagram commute. What I'm trying to say is actually F tensor 1m is actually equal to G prime inverse composed with F tilde composed with G. So by the construction of these maps, this is just how these diagrams fit together. And that's actually very nice because it's clear that G and G prime are isomorphisms. So that means that they're both injective. And so it's not hard to see that F tensor identity is, injective. Let's start over. So I'll say that M is flat if and only if I'll say all these maps of the form F tilde 1m are injective. But that's the same exact thing as saying all of these F tilde are injective. But remember how we said before that that means that all the mi are flat. And so we are done. Okay? So I think that tensor product is very strange and very abstract. Sometimes it's better to work with direct sums, and it's nice because we have such a natural isomorphism. The direct sum commutes with the, tensor product distributes over direct sums. Things work very nicely. Okay, any questions?
Yeah, I totally agree that as long as we can distribute the tensor product with the direct sum, you already took the benefit from there. But still, inside of each mi, still the tensor product is mysterious, as you said. So we actually cannot still know.
It's very strange, but very, very powerful. Okay, so if you don't mind, I will move to question number 5. So again, so let A be a ring. Says that prove that A bracket X is flat. How do I prove that A bracket X is flat? So how would I do this? So this is the benefit of, in my opinion, of working through every question from this textbook, because many of the questions you can use exercises beforehand to solve them, and things become very easy because you already did so much of the work. So let's start. So again, let A be a ring. I need to prove that A bracket X is flat. So how do I do that? So first step is, it's clear that A is a flat A module as given, let's say, A modules, let's say P and Q, and an injective map. I'll say F going from P to Q. We have that F tensor 1A is also injective. Why is that? Because, well, like we said in question number 4, there's going to be a way to relate this to an easier isomorphism. I'm sorry. How about I say P tensor A, Q tensor A, F tensor 1A. I don't know how the tensor products work. It's very strange and abstract to me. But I do know that there is an isomorphism from P tensor A to the nicest isomorphism to P. And I know that Q tensor A has a very nice isomorphism to Q, and by this G prime. So actually, G maps P tensor 1 to P, or I'll say P tensor A to A times P, and similarly G prime maps Q tensor A to A times Q. I'm not doing the full proof because I haven't proved these are linear maps because I didn't use the bilinear property yet, but don't worry about it. So using the same method we did in question number 4, there is a commutative diagram, but actually F twiddle in this case is actually just F. And so in this case, F tensor 1A is injective if and only if F is injective. But we already said it was injective here. So it's almost done because we have proven that A is a flat A module. Okay, great. So A is a flat A module, but I don't want to prove A is a flat A module. I want to prove A bracket X is a flat A module. So actually, step 2 is proving A bracket X is just the direct sum of countably infinitely many A's. How would you do that? Well, it's very simple. So
So on the right-hand side of the direct sum, did you put A with something in your step 2?
No. I want infinitely many copies of A.
Just A. Got it.
Just A.
Mm-hmm.
How do I prove this? Well, so just take a polynomial A0 plus A1x. There is a finite end to this, and it maps it to A1, AM, but then make everything else 0. Infinitely many, countably infinitely many zeros. It is not hard to, in fact, prove that clearly this is just like it's like almost like a completely equal map. Like there's nothing. I mean, it's even more than an A module homomorphism. A module isomorphism. It's literally almost the same exact sets. Phi is in fact an isomorphism. So A bracket X is in fact isomorphic to countably infinitely many copies of A.
Yeah, as long as we are not considering the algebra structure, this is clear.
Yeah, I mean, it's even more strong. It's even stronger than a group homomorphism, I think. So actually, A bracket X is a direct sum of infinitely many copies of A. And in step 1, I proved A is flat. So by question number 4, I'll say, so A bracket X is a direct sum of flat A modules. So by question number 4, A bracket X is a flat A module. So we're done. So the difficult question was actually proving question number 5. Question number 4. Question number 5 is simply a corollary to question number 4. Okay, so if there are no questions, let's move on to question number 6. So question number 6 asks, so I will not write the whole question. Sorry. Let A be a ring, and so let's say let M be an A module. I will say define M bracket X to be the set of polynomials with coefficients in the module M. And so I'll say N is finite, integer, N is a non-negative integer. So the question is not only proving that M bracket X has an A module structure, they also want you to prove that M bracket X is isomorphic to A bracket X tensor product M. So how would you do that? Well, I'm not going to prove it is has an A module structure. It's I think it would be obvious what the A module structure is when I in fact prove this isomorphism. I know that doesn't make sense. First, you should prove they're in fact modules before you make an isomorphism, but it's clear. If not, I encourage you to try it as an exercise. So I'll say that M bracket X is a group by addition. You can check that the group is in fact a binary. It's in fact a binary operation. There are inverses. Everything's associative, and the group action by A, I'll say it should be the obvious one. I don't think it's hard to check the axioms that this in fact is an A module. So try it out. But the a little bit more complicated question is to prove the isomorphism. So long as you're happy that I can just leave the proof of that to as an exercise, let's move on to proving that this is in fact an isomorphism. How do I do that? So I don't know what this is, but I do know what this is. This is a tensor product of two A modules, but remember, A bracket X is the same thing as infinitely many copies of A. And so, again, remember that the tensor product distributes over the direct sum, just like how multiplication distributes over addition. So instead of having this square bracket here, it's actually, I can actually move it this way. This was a proof in the textbook. And so now I have the direct sum of modules of this form. But I also know that for any A module M, that we have this isomorphism. So this here is isomorphic to infinitely many copies of M. But I mean, this is precisely what we proved in question number 5, that this is precisely M bracket X. Like the map is M naught MRX to R just M naught, M R, 0, 0, forever. It's the same map, but you can also see it this way, the steps we did over here. So we have in fact proven that M bracket X is in fact equal to infinite many copies of M, but that is in fact also equal to, bidirectional, nope. Here I should have tensor product. And so again, we are done. So again, like I said, if you work on these questions one after the other, it's clear how they relate to each other. Any questions?
Yeah, as long as we just care the module structure, the idea is so clear and precise. I like it.
Yeah, the tensor product is a very natural operation after you learn about it. But before, it's very abstract. But if you start working with it, it seems so natural.
If we care about the algebra structure, then everything will be broken over here. I mean, even all those isomorphisms that you use, we cannot simply use it.
Right. Yeah, using the theorems is very important. Yes. So let's move on to question number 12, and then we will go back to question number 9 if we have time, because there's a construction I have not yet defined, but it'll be okay. How about I say, sorry. So I'll say let M be a finally generated A module. And let's say phi going from phi going from M to A to the N is a surjective A module homomorphism. So I want to prove that the kernel of this map is also finally generated. So how do I do that? Take a look at my notes. Okay, so how would I do this? So let A be a ring. M is an A module. And let's just say N is just some non-negative integer, and let's say phi going from M to A to the N is surjective. So what do I do? So let's say AN to be written as something like this. Right? So let's just say A to the N has a basis E1, E2, E3, all the way up to En. Great. So I have that phi is surjective. So I say that I'll say for each I between 1 to N, there is an element, I'm sorry, not EI, UI in M such that phi of UI is EI. Okay, great. And so then what does that mean? Okay, so now you have these UIs. That's not going to be the basis of the kernel. I'm going to use that to make a basis for the kernel. I will say let M be in M. M, capital M, the module, means nothing. But I do know what happens to M when it gets sent to AN. So I don't know what phi M is, but it is a linear combination of elements of the form EI, because EI is a basis of A to the N. But remember, this is just EI is the same as E1 is the same as phi of U1, E2 is the same as phi of U2, and we have En is the same as Un. Okay, that's what I got from the surjectivity of the map. But remember, AI are elements of the ring, and this is phi is a module homomorphism, so the A's can move inside like this. Okay, so we have sum of n different elements like this, but remember, this is just a group homomorphism, so this is A1, U1 plus A2, U2 plus AN, UN. Okay, so now it's clear to see that this is equal to this. So their difference is 0. What is phi of M minus phi of A1, U1, AN, UN? This, because again, it's a group homomorphism, I can make it into one single element inside the parenthesis. This is A1, U1, A2, U2, AN, UN. This is equal to 0. Okay, now what? So this means that M minus A1, U1 minus A2, U2, AN, UN is in the kernel of phi. So I will say that actually M is equal to all this plus some K, where K is in the kernel of phi. I don't know what K is, but this is what the set theory has shown me. So actually, M was a general element of capital M. This means that M is inside the subgroup of U1, U2 to UN plus this kernel phi. Okay, but actually, these elements are inside M, and this set kernel is inside M. We actually have an equality. So we have an equality like this. Also, what is this intersection? I claim this intersection is trivial. So how can I prove that this intersection is trivial? I will let A1, U1, AN, UN be in the kernel of phi. So not only is this in here, but it's also inside the kernel. So that means that if I take phi of this group, this element, by the fact that it's an A module homomorphism, I can split it up this way. this is equal to 0. But remember, what was phi of u1? Phi of u1 was e1. What was phi of un? It was en. This is equal to 0 in the direct sum. So if it's 0 in an, the direct sum, this must be the 0 element. There's no other possibility. That means that if what I said before was true, this element is precisely 0. Great. So actually, m is equal to not only this, it's actually equal to the direct sum with this in the kernel phi. So now what? Here it is finally generated. This is finally generated. So then this must be finally generated, because the size of the basis of m will be the size of this, the basis of this, plus the size of this basis. This has size less, the basis of this has size less than or equal to n, so this must also be finite. And so we are done. So the kernel is also finally generated.
So I totally agree with the idea and the proof and all rigorous arguments. I really like it, but it makes me wondering that. So first you write down m as just a sum. So
where?
I mean, you write down m as a sum of the span of our UI with the corner, and then you show that it should be the direct sum. My question is, without showing direct sum, isn't it sufficient to already imply the result?
Probably.
Yeah.
This is probably too much work. But
yeah, I totally agree. Yeah, this is correct. Yeah, absolutely correct. But
yeah, it's probably too much work, but you know me, I'm very detailed, but it's probably unnecessary. Like you said, you're right. So I might probably be done here. Yeah.
It might behave weirdly, but I'm not sure. Yeah.
Yes, that's what I was worried about. So I just said it. I just did the rest to be sure.
Yeah. Perfect. Yeah. Thanks for that detail.
Yeah. Okay. So I have one last question to go over. But before that, let's go over a definition. Let A be a ring, and let's say M prime, M double prime are A modules. I will say that double prime 0. This is an exact sequence if, let's say, F is injective, G is surjective, and let's say kernel of G is equal to the image of F. Okay, this is extremely fundamental. This comes up in algebra, topology, number theory, every different type of math. That being said, let's try to work on number 9. Sorry. Let I said before, be a short exact sequence. Prove that if the modules on the left hand and right side are finally generated, then so is M. I'll say then M is finally generated. How do I prove this? How do I solve this? So let this be a short exact sequence. We'll not write down the details. So let's say this is a short exact sequence. I will say that M prime is generated by, I'll say M1 prime, M2 prime, and let's say M prime sub A. Okay. And so let's say M double prime is generated by M1 double prime, M2 double prime, M double prime B. So I don't know what any of these sets look like. It's just really abstract. So we have to show that M is finally generated. I will say that by abusive notation, I will call this I map. I will call this pi. I will say that I of M prime, because I is injective, I of M prime is isomorphic to M prime. I would just say they're equal. It's 100% the same thing. It's no big deal. So let's just say that forget M prime as being a distinct module. Let's just say it's a submodule of M. Okay, so now what? Let's say pi is surjective. So there exist M1, M2, MB in M such that pi of Mi, I'm sorry, let's not use I because I was already used. I'm sorry, pi of Mj equals M double prime J for all, let's say 1 less than or equal to J, which is less than or equal to B. Okay, so there's that. And then I claim that M is generated by these M1s all to MBs. So I'm talking about these go down here. And then also these M1 primes, M2 primes, and A primes. So again, I'm sorry, my iPad's stuck. These M1 prime, M2 prime come from here. That's M prime. But I'm saying M prime is just a subset of M. It's by abusive notation, it's the same exact thing. So how do I prove this is true? So again, let M be in M. I don't know what it is. Then I have that pi of M lives in M double prime. I don't know what pi of M is either, but I do know it is equal to, I'm sorry, I'll say R1 M1 double prime plus R2 M2 double prime plus R B M B double prime, where Ri is in A. Okay? So we have this idea because M1, M2, MB double prime make a basis for M. So I don't know what that all means, but I do know that there's another way to express this. M1 double prime is the same as pi of M1. M2 double prime is the same as pi of M2. And MB double prime is the same as, pi of MB. Okay? But again, this is an A module homomorphism. I can rewrite it this way. This is an A module homomorphism, so I can write it this way. But what was this equal to? It's equal to pi of n. Okay? So now let's take the difference between this and this. Pi of m minus pi of r1 m1 rb mb is the same as pi of the difference between these elements. But what is that equal to? That should equal 0. So that means m minus r1 m1 this is in the kernel of pi. But the kernel of pi is the same as the image of I. That's the same thing as I of m prime. But that's just m prime inside m. So this m prime is generated by all these, I'll call it S1, S1, M1 prime, S2, M2 prime, SA, M, A prime. So M is equal to R1, M1 plus RB, MB plus S1, M prime plus SA, MA prime for some R1, RB, and S1, SA inside the ring A. But now what? So that means that this module M, because every general lowercase m is a linear combination of elements of the form M1, M2, MB, M1 prime, M2 prime, MA prime. So every general element lowercase m is written as a linear combination of M1s to MBs, M1 primes to MA primes. That's fine. But also, all these M's, MBs, and M1 primes and MA primes are actually elements of A. So we actually have an equality. And this is a finite set. This is a finite set of generators, so we are done. So it was very important that this is true. If these generating elements are not elements of M, you cannot make any conclusion, but they are because of the construction of the exact sequence. So we actually have an equality, and so M has a basis of size less than or equal to A plus B, and that's finite. So M is finitely generated. Okay, and we're done. So I think that's a good couple of exercises that we've done for today. I think we can stop here.
Yeah, just one comment that I kind of thought is, so I think first just map the generator M to M double prime, which is surjection pi. So
Yep.
the outside of the surjection, it should be written by the corner of that map, which is identify the image of M prime, which I mean the image of I, so
Yep.
that we already have the control of all those generators. So
Exactly.
yeah.
Exactly. The short exact sequence has a way to relate the generators very cleanly.
I like your argument as well. Yeah, thanks. I will stop there.